Hey, my friend. If your mind is tired and you're looking for something calm to drift off to, you're in the right place. Tonight we're diving into the oldest light in the universe. Gently, slowly, and just enough to help your thoughts unwind. So settle in, get comfortable, and let's begin. Chapter 1. The Universe Before Light, a hot, opaque beginning. In the very beginning, the universe was not the vast, silent expanse we see today. It was a place so dense, so hot, and so tightly packed with energy that nothing resembling light could move freely through it. What we call light today was present even then, but it was trapped, scattered endlessly by a fog of charged particles that filled every corner of existence. Understanding this early state of the cosmos is essential for understanding why the oldest light we can observe, the cosmic microwave background, exists at all. To see how it formed, we must travel back to a time when the laws of physics, though unchanged, played out against conditions completely unlike anything we experience in the modern universe. For a long stretch of its earliest history, the universe was dominated by a glowing plasma made of electrons, protons, and photons. A plasma is a state of matter where particles are so energetic that they cannot form stable atoms. In this early epoch, temperatures were so high that any attempt of an electron to bind to a proton was immediately undone by a high-energy photon striking the pair and knocking the electron free again. Because so many photons were present and because their energies were extremely high, this separation happened constantly. Electrons and protons were everywhere, but the idea of a neutral atom simply did not exist yet. Without neutral atoms, space behaved like an almost perfect fog of charged particles. Photons, the particles of light, could not travel very far without interacting with one of these charged particles. In this early era, photons did not travel in straight lines across the universe. Instead, they constantly bounced from electron to electron in a process called Thomson scattering. As soon as a photon moved a tiny fraction of a centimeter, it collided with a free electron and changed direction. It could not move freely, could not carry information, and could not leave behind a clear imprint of the state of the universe. Light existed, but its motion was chaotic, tangled, and endlessly redirected. This made the universe fundamentally opaque. If someone could have floated inside this early plasma, they would not have seen anything resembling darkness, or stars, or empty space. Everything would have glowed with an intense, uniform brightness, like standing inside a blast furnace that extended in all directions. However, they would not have been able to see far through this brightness because photons were trapped in place and unable to reach their eyes in straight paths. Sight itself, as we understand it, would have been impossible. The early universe did not allow transparency. It did not permit long-distance vision or any transfer of clear electromagnetic information. Everything was constantly mixing, constantly interacting, and constantly obscured by this sea of charged particles. The reason this happened has to do with the fundamental relationship between temperature, energy, and matter. Temperature is a measure of how much kinetic energy particles have. When temperatures are extremely high, particles move rapidly, collide frequently, and cannot remain bound together. In the early universe, temperatures were so extreme that electrons and protons simply could not form hydrogen atoms. Whenever they tried, a photon with enough energy to disrupt the bond was bound to strike them almost immediately. Hydrogen, the simplest atom, could not survive. Without atoms, the universe had nothing solid, nothing neutral, and nothing that interacted weakly with light. During this period, the universe was expanding. The expansion did not just create more space, it also stretched everything inside it. When space expands, photons inside it are stretched as well. A stretched photon has a longer wavelength, which corresponds to a lower energy. As expansion continued, the photons gradually cooled. Because photons dominated the energy content of the early universe, the temperature of the cosmos as a whole decreased through this expansion. However, in those extremely early stages, the cooling was slow relative to the enormous temperatures involved. Even as the universe expanded, it took a very long time for temperatures to fall enough to allow new kinds of physics to take place. This early stage is sometimes called the photon-baryon fluid. Baryons, in this context, are the protons and neutrons that would later form atoms. In this plasma, photons had such high pressure that they resisted compression. Whenever gravity tried to pull matter into slightly denser regions, the photons pushed back, creating pressure waves. These waves oscillated like sound waves in a fluid. At the time, these oscillations left no visible imprint because nothing was transparent enough to record them. However, these ancient pressure waves would later become critical pieces of information imprinted on the cosmic microwave background. Another important component of this early era was the role of neutrinos. Neutrinos are extremely weakly interacting particles that were created in enormous numbers early in cosmic history. They do not scatter off charged particles the way photons do, and therefore they decoupled, meaning they began to travel freely far earlier than light did. Although neutrinos had a subtle effect compared to photons, their presence helps scientists today model how energy and matter behaved in the early plasma. Their existence is another reminder that the universe was already complex even before atoms could form, filled with many different species of particles whose interactions shaped the path forward. Despite the incredible density and temperature of the early cosmos, the universe was remarkably homogeneous on large scales. Tiny differences in density existed from place to place, but overall, the plasma was almost perfectly uniform. These small variations are thought to be remnants of quantum fluctuations that were stretched across astronomical distances during inflation, an extremely rapid expansion that occurred long before the plasma state. These slight differences in density would eventually grow into galaxies, clusters, and cosmic structures, but at this early stage, they were too small to affect anything visually. The universe looked nearly the same in every direction and would remain that way for a very long time. As expansion continued, something subtle but important happened. Because photons dominated the energy content, they governed how quickly the universe expanded. Over time, as the universe cooled and baryons became increasingly significant compared to radiation, the balance of forces began to shift. Gravity could begin to gather matter more effectively, and photons began to lose their ability to prevent growing structures. However, this shift did not yet free the photons themselves. The universe remained opaque because free electrons were still everywhere. The transition from this opaque state to a transparent one would eventually come from the interplay of cooling and atomic physics. As photons lost energy due to cosmic expansion, they eventually reached a point where they no longer had enough energy to disrupt newly forming atoms. Once this threshold was reached, hydrogen atoms could finally form and survive. But in Chapter 1, we remain just before that moment, in the final stages of the opaque universe, when light existed everywhere but was imprisoned within a fog of charged particles. During this time, the mean free path of a photon, the distance it could travel before colliding with an electron, was incredibly short. Photons zigzagged constantly, interacting tens of billions of times per second. Each interaction erased any record of their past, preventing them from carrying directional or spatial information. This is why no electromagnetic memory from the earliest universe survives. Photons erase themselves through constant scattering. Only when the fog lifted could photons begin to travel in straight lines, carrying with them a snapshot of the universe as it existed at that precise moment of liberation. This era also highlights the profound difference between transparency and brightness. Although the early universe was filled with light, it was bright in an entirely different sense than our modern understanding. It was bright because everything was glowing at extremely high temperatures, but not bright in a way that allowed illumination, shadows, distance, or clarity. Transparency requires that light be able to travel unimpeded from one location to another. Before neutral atoms formed, no such travel was possible. Light existed, but clarity did not. In this sense, the early universe was bright and dark at the same time, bright in content, dark in function. Another important aspect of this early stage is related to entropy. Although the universe was extremely hot and energetic, its overall entropy was surprisingly low compared to today. This meant that the early plasma was in a very ordered state. Even though conditions were extreme, the nearly perfect uniformity of the plasma is a signature of this low entropy. Only after expansion allowed matter to decouple, gravity to clump matter, and photons to move freely did the universe begin to evolve toward higher entropy states. The emergence of structure, galaxies, stars, and planets required the universe to move away from the smoothness of the early plasma. But that transition could only occur once photons stopped scattering so frequently. As the universe continued to cool, the stage was set for one of the most important events in cosmic history. Electrons would soon bind to protons, forming stable atoms for the very first time. Once this occurred, the fog would lift. Photons would decouple from matter and begin their journey across the cosmos. In doing so, they would carry with them an image of the universe at that exact moment. A faint glow stretching across all directions, forming what we now call the cosmic microwave background. For now, in this first chapter, we sit at the edge of that transformation, looking at a universe filled with light that cannot yet shine. It is a place where matter and radiation are locked together in constant motion, a place where the concept of seeing has no meaning, a place where the universe is preparing to reveal its earliest visible memory. This opaque beginning is the foundation upon which all later cosmic structure rests. As you let these ideas settle in your thoughts, allow yourself to imagine this early universe not as something chaotic or overwhelming, but as a warm, dense glow of potential waiting to unfold. Just as the universe slowly cooled into clarity, your own mind can let go of the noise of the day and drift toward calm. You are part of this long cosmic story, and in the quiet of this moment, you can rest in its gentle continuity. Chapter 2. The moment of transparency, how the first light was set free. There comes a moment in the history of the universe when everything changes at once, not through sudden violence or dramatic rupture, but through a quiet shift in conditions that had been unfolding for a very long time. Before this moment, the cosmos existed as a dense and glowing plasma where light could not travel freely. After it, the universe became transparent for the first time. Photons that had once been imprisoned in an opaque fog suddenly found themselves liberated, able to stream across space without being scattered at every step. Those same photons continue their journey today, stretched and cooled by the expansion of the universe, forming what we now see as the cosmic microwave background. Chapter 2 explores this transition with scientific care, focusing on how physical laws allowed the universe to become transparent, and why this transformation defines the earliest visible moment in cosmic history. During the plasma epoch, electrons and protons could not remain bound together because the universe was too hot. A single electron or proton did not experience heat the way we feel it on Earth. Instead, temperature reflects how much kinetic energy particles have. High temperatures mean that particles move at extremely high speeds and collide frequently. In the early universe, collisions were so energetic that any attempt by an electron to bind to a proton and form a hydrogen atom was immediately undone. Photons struck the newly forming pair with enough energy to separate them again. At this stage, matter existed only as free charges suspended in a sea of intense radiation. As the universe expanded, its temperature dropped. Expansion does not cool the universe in the same way an object sheds heat. Instead, the stretching of space itself stretches the wavelengths of photons, reducing their energy. When photon energies drop, the average kinetic energy of particles decreases. This slow cooling is essential. The universe did not suddenly reach a temperature where hydrogen could form. Instead, it approached that threshold gradually as expansion continued and photon energies decreased. Eventually, the temperature dropped to a point where many photons no longer had enough energy to dislodge electrons from newly forming atoms. At this stage, electrons began to bind with protons in a process called recombination. The term might sound like something is being reassembled, but in fact, it reflects the first formation of neutral atoms on a cosmic scale. Hydrogen atoms could now survive long enough to remain intact. Every time an electron bound to a proton, a photon was released, contributing to the radiation field in the universe. But now the growing population of neutral atoms changed the behavior of light. When electrons exist freely in a plasma, photons scatter off them constantly. When electrons bind to protons to form hydrogen atoms, they no longer scatter photons in the same way. Neutral hydrogen does not interact with photons nearly as strongly. This meant that as more and more electrons became bound into atoms, the universe began to lose the fog that had previously trapped light. This transformation did not occur everywhere in the universe simultaneously, but the change was extremely rapid on cosmological timescales. Once enough neutral atoms formed, scattering rates dropped dramatically, and photons were suddenly able to travel long distances without being deflected by free electrons. This moment is referred to as photon decoupling, because photons decoupled from matter and began traveling freely. The phrase decoupling is precise. Before this moment, photons and matter behaved like a single fluid. Afterward, photons behaved independently. At the instant of decoupling, photons carried with them the conditions of the universe as it existed at that time. This is why the cosmic microwave background is often described as a snapshot of the early universe. It reflects the moment when light was no longer trapped. The surface of last scattering is the term cosmologists use to describe the region from which the earliest free-traveling photons originated. It is not a physical surface like the surface of a star. Instead, it is a shell surrounding every observer in the universe, representing the last place where the photons we detect today interacted with matter. Because photons travel at a constant speed through space, and because space has expanded immensely since their release, we see this ancient light arriving from all directions, forming a sphere of information centered on us. Observers in other galaxies see their own sphere, shaped by the same physics but centered around their position. When the universe transitioned from opaque to transparent, the drop in scattering allowed temperature variations in the plasma to become imprinted in the light. Before decoupling, photons were unable to carry information about matter distribution because constant scattering erased their history. After decoupling, photons traveled in straight lines, preserving the shape of the last density fluctuations they encountered. Those fluctuations were incredibly small variations in the density of baryonic matter. They were imprints of earlier physical processes, including pressure waves in the photon-baryon fluid. As these photons traveled through space, their slight differences in temperature survived. Today, when astronomers map the cosmic microwave background, they see these tiny temperature variations as faint ripples across the sky. During recombination, the universe also experienced a drop in the ionization fraction, meaning that free electrons became increasingly rare. Once the majority of electrons had become bound into hydrogen atoms, the number of free electrons dropped by several orders of magnitude. This reduction was enough to essentially end Thomson scattering. The universe did not become perfectly transparent at once. Some residual scattering persisted, but it became negligible compared to the earlier epoch. Scientists study this process using well-established physics that combines thermodynamics, atomic structure, and cosmological expansion. Modern observations of the cosmic microwave background confirm that the moment of transparency was not instantaneous. It occurred over a relatively narrow but non-zero band of time, which corresponds to a range of redshifts rather than a single sharp point. Nevertheless, the transition was rapid compared to the overall age of the universe, and the imprint it left is extremely clear. Cosmologists use detailed models to determine the temperature evolution associated with recombination. They also analyze how the distribution of matter at that time influenced the patterns seen in the cosmic microwave background. The moment of transparency did more than free photons. It also allowed matter to collapse under gravity more effectively. Before recombination, the pressure of radiation prevented small density variations from growing. After recombination, baryons could fall into gravitational wells formed primarily by dark matter, which had been evolving independently because it did not interact with photons. The first steps toward galaxy formation occurred only after the universe became transparent, because only then could matter respond to gravity without being held up by radiation pressure. The liberation of photons also marked the end of the radiation-dominated era. Before recombination, radiation pressure influenced cosmic dynamics strongly. After recombination, matter became the dominant factor shaping structure growth. This shift did not mean radiation disappeared or became irrelevant. The cosmic microwave background is a reminder that radiation remains an integral part of the universe. But from this moment forward, it no longer dictated the evolution of large-scale structures. Scientists have studied the physics of recombination in extraordinary detail. Atomic transitions, ionization energies, and scattering cross-sections are well understood through quantum electrodynamics and classical electromagnetism. Computational models accurately simulate how electrons bound to hydrogen nuclei, how photons decoupled, and how temperature fluctuations evolved. The remarkable agreement between theoretical predictions and observations from satellites such as COBE, WMAP, and Planck confirms that the moment of transparency is one of the most well-understood transitions in cosmic history. Even though this chapter focuses on the early stages of recombination, it is important to note that helium also played a role. Helium nuclei formed earlier, during primordial nucleosynthesis, and helium atoms captured electrons around the same general period as hydrogen. These processes contributed to the overall decline in free electrons. However, hydrogen dominated the matter content by mass and had the largest effect on the opacity of the universe. As hydrogen atoms formed, the most dramatic reduction in scattering occurred. After the universe became transparent, the photons that had once been trapped began their long journey across space. They traveled in every direction, filling the cosmos uniformly. Because the universe expanded as these photons traveled, their wavelengths stretched from those of visible or infrared photons to the microwave wavelengths we observe today. The cosmic microwave background is not only a window into the moment when the universe became transparent, it is also a record of how much space has expanded since that moment. Its temperature today reflects the accumulated stretching of light over cosmic time. This transformation from opacity to transparency reveals a deep connection between the microscopic world of atomic physics and the macroscopic world of cosmology. The universe became transparent because electrons could finally bind with protons, forming simple atoms. This small-scale process allowed photons to travel uninterrupted across the vastness of space. The clarity of the universe depended on the structure of hydrogen. The first visible moment depended on the behavior of a single electron orbiting a single proton. A shift in atomic physics created a shift in cosmic visibility. Standing at this transition in our imagination, we can appreciate how everything that followed, galaxies, stars, planets, and all chemical complexity, rests on a foundation built during the time when the universe cooled enough for atoms to form. The moment of transparency is not just a phase transition. It is a turning point in the history of cosmic structure. Without it, no photon from the early universe would reach us today. Without it, the deep patterns that seeded galaxies would have remained hidden. As this chapter draws to a close, it is worth stepping back from the physics for a moment. The earliest light in the universe has been traveling across expanding space for more than 13 billion years, yet it still reaches us gently, whispering the shape of the universe as it once was. In its faint glow is the memory of a cosmos that had just become visible for the first time. There is something comforting in knowing that the universe carries its history with such quiet persistence. And as you listen now, perhaps you can let that ancient calm settle around you, reminding you that even the most turbulent beginnings eventually give way to clarity. Chapter 3: What the Cosmic Microwave Background Actually Is. The cosmic microwave background is often described as the oldest light in the universe, but this simple phrase hides a great amount of scientific detail. This light is not just old, It is ancient in a way that stretches the meaning of the word. It comes from a time when the universe had only just become transparent, when the first atoms had formed and photons were no longer trapped in an opaque plasma. Because this light has been traveling across expanding space for more than 13 billion years, it carries with it a precise record of the conditions that existed when the cosmos was still extraordinarily young. Understanding what this radiation actually is requires moving carefully through several layers of physics. The nature of blackbody radiation, the behavior of photons as space expands, the meaning of temperature in an evolving universe, and the significance of the tiny variations imprinted on this ancient glow. The cosmic microwave background is a form of electromagnetic radiation. It is not a glow from stars, nor is it radiation emitted by gas, dust, or galaxies. It is not a scattered echo or a faint afterglow left behind by later cosmic events. Instead, it is radiation that originates directly from the moment when photons first became able to travel freely through space. It is a fossil imprint of that transition, preserved across cosmic time. The radiation itself is extremely uniform, filling every direction with nearly identical intensity. It forms a perfect backdrop to the entire sky. Even if the universe had no stars or galaxies, the cosmic microwave background would still exist, shining softly as a nearly uniform bath of microwave light. One of the most striking properties of the cosmic microwave background is its spectrum. When measured with sensitive instruments, the radiation matches the spectrum of a near-perfect blackbody. A blackbody is an object that emits electromagnetic radiation solely according to its temperature, with no distortions or gaps in its emission curve. The early universe, when it was still a hot plasma, behaved like an almost ideal blackbody. Because photons were constantly interacting with matter in that plasma, they reached thermal equilibrium, meaning they adopted a distribution of energies determined only by temperature. When the universe became transparent, this distribution was imprinted on the radiation. As the universe expanded and cooled, the entire blackbody spectrum shifted to longer wavelengths, but its shape remained intact. This is a key piece of evidence that the cosmic microwave background comes directly from the early thermal history of the universe. Today, the cosmic microwave background corresponds to the spectrum of a blackbody at just a few degrees above absolute zero. The cooling of this radiation is not due to the loss of energy through interaction, because once photons were freed from scattering, they interacted very little with matter. Instead, the cooling is a direct result of the expansion of space itself. As space expands, the wavelength of every photon traveling through it is stretched. A stretched wavelength corresponds to lower energy. Therefore, the radiation cools in proportion to the expansion. Because this process affects every photon equally, the blackbody spectrum remains intact, simply shifting to longer wavelengths as time passes. This predictable cooling allows scientists to infer how much the universe has expanded since the moment of photon decoupling. The cosmic microwave background we observe today is in the microwave region of the electromagnetic spectrum because its wavelengths have been stretched by a factor of more than 1,000 compared to their wavelengths at the moment of decoupling. Originally, these photons had energies corresponding to visible or near-visible light. After billions of years of cosmic expansion, their wavelengths now fall in the millimeter range. This shift does not alter the information encoded within the radiation. Instead, it changes the energy scale at which we detect it, moving it from the optical range into a much cooler and gentler part of the spectrum. Although the cosmic microwave background is extremely uniform, it is not perfectly smooth. Instruments such as the COBE satellite first revealed that the radiation contains tiny variations in temperature. Later missions, notably WMAP and Planck, measured these variations with extraordinary precision. The temperature differences are incredibly small, much less than 1 part in 100,000, yet they carry immense scientific significance. These tiny fluctuations reflect small differences in the density of matter at the moment of photon decoupling. Because photons could travel freely after that moment, they preserved a record of the density variations imprinted on the plasma. Over cosmic time, these variations became the seeds of all large-scale structure. Regions slightly denser than average eventually grew into galaxies and clusters of galaxies. Regions slightly less dense became cosmic voids. The cosmic microwave background thus provides a map of the universe in its earliest observable form, capturing the initial conditions that would later unfold into the vast structures we see. Another important feature of the cosmic microwave background is its isotropy. In almost every direction, the temperature is nearly identical. This uniformity supports the idea that the early universe was highly homogeneous on large scales. The fact that different regions of the sky, separated by distances far too great to have been in causal contact according to simple expansion models, nevertheless share the same temperature, is one of the observational motivations behind the theory of inflation. The inflationary model proposes a very rapid expansion early in cosmic history that would have allowed distant regions to have once been close enough to interact and reach thermal equilibrium before being driven far apart by expansion. The uniformity of the cosmic microwave background provides strong support for a period of inflation, even though the radiation itself was released much later. The cosmic microwave background is observed as a diffuse glow, but its detection requires specialized instruments. Human eyes cannot see microwave radiation. Instead, detectors on satellites measure microwave intensity at different parts of the sky. These measurements must be extremely precise to detect fluctuations at the microkelvin level. The fact that the spectrum matches a nearly perfect blackbody curve with exceptional accuracy is one of the strongest confirmations of the Big Bang model. No alternative model has been able to account for the precise shape and uniformity of the cosmic microwave background spectrum. The radiation also contains subtle additional features beyond temperature variations. One of these features is polarization. Polarization refers to the orientation of the electric field component of electromagnetic waves. When photons scatter off electrons, they can acquire a preferred orientation, leading to measurable patterns of polarization. The cosmic microwave background contains both so-called E-mode polarization, which arises directly from density fluctuations, and B-mode polarization, which can arise from gravitational waves or lensing effects. Detecting these different modes allows scientists to infer additional details about the early universe, including the distribution of matter and potentially even the influence of primordial gravitational waves predicted by some inflationary models. Although these polarization features are very faint compared to the temperature fluctuations, they contain valuable information about the physical processes shaping the early universe. Another important aspect of the cosmic microwave background is the way it provides a direct measurement of the geometry of the universe. The pattern of fluctuations on the sky, specifically the characteristic angular scale of the first acoustic peak in the power spectrum, reveals that the universe is extremely close to spatially flat. Spatial flatness means that, on large scales, the geometry of the universe follows Euclidean rules without significant curvature. This finding is consistent with predictions from inflation and helps constrain models of cosmic composition and evolution. Although the cosmic microwave background is extremely uniform, it also contains minor asymmetries that continue to puzzle researchers. Some of these include the so-called cold spot and certain hemispherical differences in power distribution. These features may be statistical fluctuations, but they may also point to new physics or large-scale cosmic structures. While the cosmic microwave background is one of the most well-understood pieces of observational evidence in cosmology, these subtle anomalies remind scientists that there are still mysteries woven into the earliest visible light. The radiation does not merely illuminate the past, it also serves as a reference point for measuring cosmic motion. Because the cosmic microwave background is expected to be uniform in the rest frame of the universe, any motion of the Earth, solar system, or Milky Way relative to that frame results in a Doppler shift. This shift causes a slight increase in temperature in the direction of motion and a slight decrease in the opposite direction. This effect, known as the dipole anisotropy, provides a direct measurement of our motion through space. In this way, the cosmic microwave background acts as a cosmic compass, offering a fixed frame against which motion can be measured. Despite its importance, the cosmic microwave background is incredibly faint. The microwave radiation reaching Earth carries very little energy per unit area. It is not harmful and does not interfere with daily life. It is quiet and persistent, a gentle signal that pervades the cosmos. Detecting it required technological advances in cryogenics, microwave detectors, and calibration techniques. Once detected, however, its presence became undeniable and its significance immense. Describing the cosmic microwave background simply as the oldest light does not entirely capture its nature. It is the oldest freely propagating radiation, but before it, the universe was filled with light trapped in the plasma. What makes the cosmic microwave background special is that it is the first light that could survive, the first light that could carry information across the universe without being scattered. It is the universe's oldest visible memory. In reflecting on the cosmic microwave background, one is confronted with a profound sense of scale. The photons we detect today have been traveling for nearly the entire history of the universe, passing through expanding space with no destination other than the places where they are absorbed. Each photon carries a message from a time before stars existed, before galaxies formed, before any complex structure emerged. Their persistence is a reminder that the universe does not forget its earliest moments. It holds them gently and carries them forward. As you listen to the quiet story of this ancient light, perhaps you can feel a sense of continuity stretching across time. The photons that began their journey long before life emerged on Earth are reaching you in this moment, whispering a record of beginnings older than imagination. And in that gentle arrival, there is room for reflection, for stillness, and for the comforting thought that even across the longest distances, light finds its way. Chapter 4. How we can see the infant universe today. When we look into the night sky, the light that reaches us has traveled across immense distances. Even the nearest stars shine with photons that left their surfaces years ago. The light from distant galaxies began its journey millions or billions of years in the past. But nothing in the cosmos compares to the age of the photons that make up the cosmic microwave background. These ancient particles of light began traveling freely when the universe was still in its infancy. They have crossed expanding space for nearly the entirety of cosmic history, carrying with them a snapshot of conditions that existed long before the first star ignited. The remarkable fact that we can observe this light today rests on the interplay between the expansion of space, the transparency of the post-recombination universe, and the persistence of photons traveling through nearly empty regions for billions of years without significant obstruction. To understand how we can see the infant universe, it is helpful to imagine space not as a static container, but as a dynamic fabric that stretches over time. Photons moving through space follow the curvature of this expanding geometry. They do not slow down or lose energy by interacting with matter. Instead, they are stretched as space itself expands, and this stretching increases their wavelength. The photons that were once at visible or near visible wavelengths when the universe first became transparent are now shifted into the microwave part of the spectrum. This redshifting process allows the ancient radiation to remain detectable even after unimaginable spans of time. The cosmic microwave background would not be visible to us if the universe had not expanded in a way that allowed photons to maintain their paths with minimal interference. After recombination, when hydrogen atoms formed and the universe became transparent, the vast majority of matter existed in a neutral state with very low density. Because of this, photons encountered few obstacles. Collisions became extremely rare. Once set free, the photons traveled in nearly straight lines, deviating only through the geometrical effects of general relativity and gravitational potentials of galaxies or clusters they passed near. These gravitational interactions can slightly bend their path or change their energy, but such effects are tiny compared to the vast distance they travel. It is also essential that the universe is not infinitely old. If it were eternal and unchanging, the cosmic microwave background would have been absorbed or scattered countless times over infinite time. Instead, it originates from a specific epoch and then travels through a universe that has been growing more transparent rather than less. As the universe expands, matter becomes increasingly diffuse. Neutral hydrogen absorbs only specific wavelengths, meaning the broad blackbody spectrum of the cosmic microwave background passes through it almost unaffected. The intergalactic medium today is extraordinarily thin, with fewer particles per cubic meter than the best vacuums human technology can produce. This tenuous environment allows ancient photons to pass nearly unimpeded across distances that defy intuition. Another reason we can see the infant universe today is that the cosmic microwave background arrives from every direction. It is not emitted by a single source. Instead, it forms a spherical surface centered around every observer, representing the last place from which photons could travel freely to that observer. This surface is called the surface of last scattering. Each point on the sky corresponds to photons arriving from a different part of this ancient spherical shell. Because the universe is homogeneous on large scales, every observer, on Earth, in another galaxy, or anywhere else, would see their own cosmic microwave background centered upon them. The pattern is universal, yet the perspective is always local. Despite this universality, seeing the cosmic microwave background is not straightforward. Human eyes cannot detect microwave radiation. Observing it requires specialized instruments capable of measuring very low-energy photons and distinguishing extremely slight temperature differences across the sky. These instruments must be placed in environments where local radiation and atmospheric effects do not overwhelm the faint cosmic signal. Modern observations are conducted using satellites above the atmosphere, such as the COBE, DOMAP, and Planck missions. These observatories map the entire sky in multiple frequency bands, allowing scientists to separate the cosmic signal from foreground emission produced by the Milky Way. Seeing the infant universe also relies on the predictable physics of blackbody radiation. The cosmic microwave background exhibits a spectrum that is extraordinarily close to a perfect blackbody curve. This spectral shape allows researchers to identify the radiation's origin unambiguously. No other known process in the universe can generate such a precise and uniform blackbody spectrum across the entire sky at such a cold temperature. The fact that this spectrum remains intact after billions of years provides strong evidence that the universe has expanded smoothly and uniformly, preserving the thermal distribution imprinted during the early plasma epoch. The cosmic microwave background is not uniform in temperature. Instead, it exhibits tiny fluctuations. These fluctuations correspond to small differences in the density of the plasma at the time of photon decoupling. Observing these variations allows scientists to reconstruct the distribution of matter at a time when the universe was still extremely young. The precision of these measurements allows cosmologists to determine fundamental parameters such as the curvature of space, the proportion of ordinary matter, the density of dark matter, and the influence of dark energy. Seeing the infant universe also involves interpreting the effects that have been imposed on the cosmic microwave background by later cosmic structures. As the photons travel through the universe, they are influenced by gravitational potentials. Clusters of galaxies can imprint small distortions through the Sunyaev-Zeldovich effect, where hot electrons in galaxy clusters scatter some of the cosmic microwave background photons, slightly altering their energy. This effect does not erase the original pattern, but adds additional information that scientists can model and subtract. Similarly, the large-scale structure of the universe can bend photon paths through gravitational lensing. This bending is measurable and provides clues about the distribution of matter, including dark matter, which does not emit or absorb light. The fact that these photons can be studied today is an indication of how stable and transparent the universe has become since its early days. The physical processes that govern photon propagation are well understood. Electromagnetic radiation travels unhindered through vacuum. Ionized matter can scatter or absorb it, but the amount of ionized gas in the modern universe is extremely small outside of localized regions such as stars and nebulae. Neutral hydrogen can absorb specific wavelengths, but the cosmic microwave background occupies a range of frequencies that pass through the intergalactic medium without significant attenuation. Even the reionization of the universe, which occurred when the first stars ignited and reionized hydrogen gas, did not destroy the cosmic microwave background. It only introduced a small amount of scattering, leaving its overall structure intact. The most astonishing aspect of seeing the infinite universe is that when we look far enough away, we are not just looking at distant objects, we are looking back in time. Light has a finite speed. A photon that reaches us now has spent a measurable amount of time traveling. For nearby galaxies, that travel time might be millions of years. For galaxies near the observable horizon, the travel time is on the order of billions of years. And for the cosmic microwave background, it is nearly as long as the age of the universe itself. The cosmic microwave background thus represents the farthest back we can see using electromagnetic radiation. Beyond the surface of last scattering, the universe was opaque and photons could not travel freely. Therefore, no electromagnetic signal from earlier times can reach us. The cosmic microwave background marks the boundary of the observable universe in a very literal sense. It is the oldest electromagnetic light we can ever detect. Although the cosmic microwave background allows us to see the infinite universe, it does so in a very different way from how we perceive visible objects. We are not seeing a single moment or a single place. We are seeing a shell of ancient radiation spread across the sky. Each point on this shell corresponds to a different region of the early universe, located billions of light years away from every other region. When we observe the cosmic microwave background, we are observing the universe not as it is, but as it was at a specific moment in time, long before structure emerged. To see the infinite universe, we do not need a telescope pointed at a particular star or galaxy. Instead, we need instruments that can detect a faint, nearly uniform glow coming from all directions. This glow is not a residual effect of something that happened elsewhere. It is the direct arrival of ancient photons that have traveled for more than 13 billion years. The universe has been expanding, cooling, and evolving throughout that time, but these photons have remained coherent, carrying their early messages across the shifting fabric of space. When we look at the cosmic microwave background, we are not merely observing light. We are witnessing the first moment when the universe could bear witness to itself. Before that moment, nothing in the cosmos could record or carry information across space. After that moment, the universe became readable. It developed the capacity to preserve its own history in radiation, matter, and structure. To see the cosmic microwave background is to see the dawn of cosmic memory. And perhaps in the quiet of this moment, you can feel the weight and wonder of that continuity. Light that began its journey long before galaxies formed is reaching you now, completing a path measured not in kilometers but in epochs. In that gentle arrival lies a reminder of your place within a cosmos that remembers its beginnings. The universe holds its earliest impressions with remarkable clarity, and in listening to them, you join a story that spans more than space or time can easily convey. Chapter 5. Tiny Imperfections, the Seeds of Every Galaxy. When the universe first became transparent, it looked astonishingly smooth. The temperature of the cosmic microwave background varied by only a few parts in 100,000, and the density of matter differed only slightly from place to place. To the unaided imagination, this might seem indistinguishable from perfect uniformity. Yet in physics, perfection is rare, and these minute imperfections in temperature and density hold profound significance. They are the fingerprints of processes that took place when the universe was very young. More importantly, they are the seeds from which every galaxy, every star, and every planet ultimately formed. Without these initial irregularities, the cosmos would have remained a vast, cold, and featureless expanse. Instead, it became a universe filled with structure. These imperfections were not random noise. They were imprints of ancient fluctuations that arose long before the universe became transparent. To understand their origin, imagine the early cosmos as a fluid composed of photons, electrons, and baryons. This fluid could compress and rarefy, forming waves of pressure somewhat analogous to sound waves. Regions that were slightly denser than average would pull matter inward, but the pressure of photons would resist compression. This interplay created oscillations in the plasma. When recombination occurred and photons decoupled from matter, these oscillations were frozen into the cosmic microwave background. The peaks and troughs of these oscillations became visible as the tiny temperature variations we detect today. Even though these variations are unbelievably small, they represent differences in density that would eventually determine the structure of the universe. A region that was slightly denser than average at the moment of decoupling had more gravitational pull. Over time, as the universe expanded and cooled, these regions could attract more matter. The tiny excess drew in surrounding material, allowing density contrasts to grow. In regions where the density was slightly lower than average, matter drifted away. This process unfolded gradually, taking hundreds of millions of years to form the earliest gravitationally bound structures. A crucial component in this growth was dark matter. Unlike baryons, dark matter does not interact with photons. It does not scatter, absorb, or emit radiation. Because of this, dark matter became able to form gravitationally bound structures earlier than ordinary matter. While electrons and protons were still tightly coupled to radiation, dark matter could clump under gravity. When the universe became transparent and baryons decoupled from photons, they began falling into the gravitational wells created by dark matter. These wells acted like the scaffolding upon which galaxies would form. The tiny imperfections in the cosmic microwave background thus reflect the combined contributions of both baryonic matter and dark matter, though dark matter played the dominant role in sculpting the large-scale pattern. The temperature fluctuations visible in the cosmic microwave background are more than just isolated dots of warmth or coolness. They form a pattern across the entire sky. This pattern can be analyzed statistically to reveal information about the density of matter, the expansion rate of the universe, and the curvature of space. In particular, the angular scale of the variations shows the characteristic size of the largest pressure waves in the early plasma. These waves left imprints that later grew into clusters of galaxies and the cosmic web. The clustering of galaxies today mirrors, on vastly larger scales, the patterns recorded in the radiation from the early universe. The concept of acoustic peaks emerges from this analysis. These peaks correspond to oscillations in the plasma that had just enough time to reach certain phases before the moment of photon decoupling. Each peak represents a different harmonic, much like the overtones produced by a vibrating string or a resonating cavity. When cosmologists measure these peaks in the cosmic microwave background power spectrum, they learn how the plasma behaved and how matter and radiation interacted. From this information, they can infer the proportions of ordinary matter, dark matter, and radiation present at that early time. The precision of these measurements is extraordinary, allowing scientists to determine the relative contributions of these components with remarkable accuracy. It is striking that imperfections so small became the seeds of structures so vast. A tiny overdensity that differed from its surroundings by less than 1 part in 100,000 eventually grew into a galaxy containing hundreds of billions of stars. This transformation occurred because gravity relentlessly amplifies differences. A slight increase in density amplifies gravitational attraction, which then gathers more mass, increasing density further, and so on. This positive feedback loop continues until the region becomes gravitationally bound and eventually collapses into a recognizable structure. The formation of the cosmic web, a vast network of galaxies and dark matter filaments, is the result of this amplification process playing out on enormous scales. Regions that began as slightly denser than average grew into long filaments, while areas that began slightly less dense evolved into enormous cosmic voids. The boundaries between these regions form sheets and walls of galaxies. The universe, on its largest scales, resembles a three-dimensional web of dazzling complexity. Yet the underlying pattern is already present in the distribution of temperature fluctuations in the cosmic microwave background. The early universe contained the blueprint for the structure we observe today. These imperfections also contain clues about the earliest moments of cosmic history. Some models of inflation predict specific types of fluctuations. Inflation is thought to generate nearly scale-invariant perturbations, meaning the fluctuations have roughly the same amplitude across a broad range of scales. Observations of the cosmic microwave background show a pattern remarkably close to this prediction. Furthermore, the distribution of fluctuations is nearly Gaussian, meaning that their statistical properties follow a normal distribution. This is consistent with quantum fluctuations being stretched to cosmic scales. These findings are not only consistent with inflation, but help to constrain models of inflation and shed light on physics at energy scales far beyond those accessible to particle accelerators. Another important detail is the distinction between temperature fluctuations and polarization patterns. Temperature variations reflect differences in density, while polarization patterns reflect the directional properties of scattered light. The cosmic microwave background contains specific polarization signatures that reveal how photons last scattered off electrons in the early universe. These polarization patterns provide independent information about how the early plasma behaved. They can also reveal the presence of gravitational waves from inflation, though detecting such a signal remains an ongoing challenge. Yet even with all this complexity, the underlying message is simple. The universe requires imperfections to grow. If the cosmos had been perfectly smooth, no galaxy would have formed. Without galaxies, there would be no stars. Without stars, no planets. Without planets, no chemistry capable of supporting life. The structures we depend on for existence trace their origins back to tiny fluctuations in the early plasma. These imperfections are the cosmic seeds from which everything familiar has grown. Understanding the seeds of structure does not diminish their mystery. The fact that such small fluctuations emerge naturally from the physics of the early universe is scientifically comprehensible, yet still profound. The early universe was not a static backdrop, but a dynamic environment where quantum processes, fluid behavior, and gravitational interactions intertwined to shape the future. These interactions created a landscape that was almost perfectly uniform, but not quite. That not quite is the key to everything that followed. When we observe the cosmic microwave background, we are not just seeing temperature variations. We are seeing the universe's potential etched into light. Each warm spot represents a region where matter would eventually gather. Each cool spot marks an area that would expand into a cosmic void. The entire map is a snapshot of possibilities just beginning to unfold. And as you reflect on these ancient imperfections, perhaps you can sense a gentle truth woven into the fabric of the cosmos. The universe did not require perfection to create beauty. It required small deviations, tiny differences, faint ripples of imbalance. From them came galaxies, stars, worlds, and life itself. In the quiet of this moment, you might find comfort in knowing that even the smallest variations can lead to immense and wondrous outcomes, and that the cosmos you inhabit began with imperfections that grew into everything you see. Chapter 6: How we measure the CMB, from sounding rockets to modern satellites. To measure the cosmic microwave background is to attempt something both delicate and monumental. The radiation we seek is extraordinarily faint, arriving from every direction with a temperature only a few degrees above absolute zero. Its fluctuations are even smaller, subtle variations impressed upon the sky that differ by a fraction of a percent. Yet these tiny differences encode the structure of the infant universe, carrying information about the density of matter, the geometry of space, and the seeds of cosmic evolution. Detecting such a faint signal requires extraordinary precision, technological innovation, and careful separation of the cosmic message from all the other radiation produced by stars, planets, dust, and even our own atmosphere. The earliest measurements of the cosmic microwave background relied on ground-based instruments and sounding rockets. Ground conditions are far from ideal for detecting microwave radiation, because water vapor in the atmosphere absorbs and emits strongly at many microwave frequencies. Even in exceptionally dry locations such as Antarctic plateaus or high-altitude deserts, atmospheric interference remains significant. Nevertheless, early experiments demonstrated that the background radiation was real, uniform, and consistent with a nearly perfect blackbody spectrum. Sounding rockets extended these measurements above most of the atmosphere, giving a clearer view of the sky for brief periods. These launches provided some of the first high-quality data on the cosmic microwave background spectrum, confirming that it matched theoretical expectations for relic radiation from the early universe. Despite these initial successes, it soon became clear that the most precise measurements would require instruments above the atmosphere entirely. The breakthrough came with the launch of satellites dedicated to studying the cosmic microwave background. These missions revolutionized cosmology by providing full sky maps of temperature variations and polarization patterns with unprecedented precision. The first of these major missions was COBE, the Cosmic Background Explorer. COBE carried instruments capable of measuring the spectrum of the cosmic microwave background and mapping its large-scale temperature variations. One of COBE's key achievements was confirming that the cosmic microwave background has a blackbody spectrum with astonishing accuracy. This result is often regarded as one of the strongest confirmations of the Big Bang model. COBE also detected temperature fluctuations across the sky, revealing the first evidence of the tiny imperfections that later gave rise to cosmic structure. Although COBE's angular resolution was coarse, its detection of anisotropies was a watershed moment in cosmology. For the first time, the early seeds of galaxies were visible as faint ripples on the sky. Building on COBE's success, the next major mission was WMAP, the Wilkinson Microwave Anisotropy Probe. Launched into a stable orbit around the Sun-Earth Lagrange point, WMAP measured temperature fluctuations with far greater resolution than COBE. It produced detailed maps that allowed scientists to determine cosmological parameters with extraordinary precision. Observations of the first acoustic peak in the power spectrum, for example, revealed that the universe is spatially flat to within a very small margin. WMAP's data constrained the proportions of dark matter, ordinary matter, and dark energy. It provided a coherent and self-consistent picture of the cosmos, strengthening confidence in the standard model of cosmology. However, as advanced as WMAP was, the quest for even finer detail pushed scientists toward a new frontier. This came with the European Space Agency's Planck satellite. Planck represented a major leap in sensitivity, angular resolution, and frequency coverage. It carried instruments cooled to extremely low temperatures, allowing detectors to see faint fluctuations with minimal instrument noise. Planck surveyed the sky in multiple microwave bands, enabling scientists to separate the cosmic signal from foreground emission produced by dust and gas in the Milky Way. The result was the most detailed map of the cosmic microwave background ever produced. Planck's measurements refined cosmological parameters to remarkable precision, revealing the universe's age, composition, and geometry with an accuracy that earlier generations of scientists could hardly have imagined. To measure the cosmic microwave background precisely, detectors must be shielded from their own thermal emission. Even a slightly warm instrument produces far more radiation than the cosmic background. For this reason, satellites like Planck and WMAP used elaborate cooling systems. Some instruments were cooled to temperatures only a fraction of a degree above absolute zero. This nearly eliminates thermal noise and enables the detection of faint cosmic signals that would otherwise be drowned in instrument-generated emission. Another challenge involves separating the cosmic microwave background from other sources of radiation. The Milky Way emits microwaves through several processes, including synchrotron radiation from electrons spiraling in magnetic fields and thermal emission from dust grains warmed by starlight. These foregrounds vary across the sky and must be removed with careful analysis. Different processes dominate at different frequencies. By observing the sky in several microwave bands, scientists can model and subtract foreground emission, revealing the underlying cosmic signal. Measurement of the cosmic microwave background also requires exquisite calibration. Instruments must be precise enough to detect temperature changes smaller than a millionth of a degree. Calibration involves comparing measurements against known standards, such as laboratory blackbody sources or the predictable dipole anisotropy caused by Earth's motion through space. The accuracy of these calibrations ensures that the maps produced reflect the true cosmic signal rather than artifacts. Polarization adds another dimension to measurement. Photons in the early universe could become polarized when they scattered off electrons, creating patterns in the cosmic microwave background that carry information about the geometry and evolution of the early plasma. Detecting polarization is even more challenging than measuring temperature fluctuations. The signal is smaller, and foreground contamination from dust is significant. Nevertheless, Satellites and ground-based experiments have succeeded in mapping the polarization of the cosmic microwave background, providing new insights into early cosmic conditions and the distribution of matter. Ground-based instruments continue to play an important role by measuring specific features of the cosmic microwave background with high resolution, particularly its polarization at small angular scales. Telescopes in the Antarctic, such as the South Pole Telescope, and in the Atacama Desert, such as the Atacama Cosmology Telescope, operate at high altitudes where the atmosphere is thin and dry. These observatories complement satellite missions by targeting specific frequency ranges or angular scales. They can observe for long periods, building up sensitivity and probing the cosmic microwave background in ways satellites may not be optimized to do. Balloon experiments also contribute valuable data. By drifting high above most of the atmosphere for extended periods, balloon-borne instruments can measure the cosmic microwave background with reduced atmospheric interference. These missions serve as testbeds for new detector technologies and as platforms for targeted observations. The flexibility of balloon-based instruments allows researchers to experiment with new designs before committing to the complexity of satellite construction. One of the most significant modern challenges involves the detection of B-mode polarization, a specific pattern that can be generated by gravitational waves produced during cosmic inflation. Detecting such a signal would provide powerful evidence for inflation and offer insight into physics at energy scales unreachable by particle accelerators. Although early claims of detecting B-mode polarization were later shown to be contaminated by dust emission, ongoing efforts aim to measure this subtle pattern with increasing sensitivity. Future experiments may finally reveal whether inflationary gravitational waves left their imprint on the cosmic microwave background. Computing and analysis play an equally important role. The raw data from cosmic microwave background observations must be processed, filtered, and interpreted. Noise must be separated from signal. Foregrounds must be removed. Complex statistical tools must be used to extract cosmological parameters from the patterns in the sky. This involves solving large systems of equations, running simulations, and comparing observational data with theoretical models. The process is computationally intensive, but essential for transforming maps of microwave intensity into a deeper understanding of the universe. The evolution of cosmic microwave background measurement reflects a progression from crude instruments that could only glimpse the background radiation to sophisticated observatories capable of mapping fluctuations at extraordinary precision. Each generation of instruments has deepened our understanding, sharpened our measurements, and expanded our knowledge of the cosmos. The combination of satellites, ground-based observatories, balloon experiments, and advanced data analysis has transformed the cosmic microwave background from a theoretical prediction into one of the most precisely measured phenomena in modern science. And yet, beyond the technical achievements and the scientific breakthroughs, there is something quietly humbling about measuring the oldest light in the universe. These photons have traveled for nearly the entire history of cosmic time, untouched except for the gentle stretching imposed by the expansion of space. They arrive here now in detectors we have built, offering a message from a time when the cosmos was newly transparent. In their faint glow, we read the story of beginnings. As you reflect on this ancient journey, Perhaps you can feel the quiet continuity between that early moment and this one, and take comfort in knowing that even across such vast distances and ages, light endures, carrying the memory of the universe forward. Chapter 7. What the CMB tells us about the universe. The cosmic microwave background is more than an ancient glow. It is a record, a map, a nearly pristine imprint of the earliest moment the universe could express itself in light. While chapters before this one have explored how the cosmic microwave background formed and how it is measured, this chapter turns to a deeper, more sweeping question. What does it actually reveal? The answer reaches into nearly every domain of cosmology. From the age of the cosmos to its geometry, from the composition of matter to the influence of dark energy, from the behavior of the earliest plasma to the growth of structure over billions of years, the cosmic microwave background is the key that unlocks the universe's most fundamental properties. To begin, the cosmic microwave background serves as a cosmic thermometer. Its temperature today is just a few degrees above absolute zero, corresponding to the stretched and cooled remnant of the hot radiation present when the universe first became transparent. This temperature is not arbitrary. When combined with the known physics of expansion, it reveals exactly how much the universe has grown since that early era. By studying the spectrum of the cosmic microwave background, cosmologists can determine the scale factor, the degree to which space has stretched from that initial moment until now. This in turn provides a precise estimate of the universe's age. The steady cooling of radiation, governed by the expansion of space, indicates that the universe has existed for a time equal to more than 13 billion years. This remarkable conclusion does not rest on guesswork, but on the predictable evolution of blackbody radiation across cosmic time. The cosmic microwave background is also a cosmic photograph of density fluctuations, and from these fluctuations, cosmologists extract information about the universe's composition. One of the striking findings is that ordinary matter, the kind made of protons, neutrons, and electrons, makes up only a small fraction of the total cosmic content. The temperature variations recorded in the cosmic microwave background reflect the behavior of the primordial plasma, including how pressure waves moved through it. These pressure waves were influenced by the density of ordinary matter and the density of radiation, but not directly by dark matter. By comparing the heights of different acoustic peaks in the cosmic microwave background power spectrum, scientists infer the amount of ordinary matter in the early universe. The result is a value that is surprisingly small. The majority of the matter that shaped cosmic structure is dark matter, an invisible component that interacts through gravity but not through light. The cosmic microwave background also reveals the influence of dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. While dark energy does not directly alter the cosmic microwave background, it affects the late-time evolution of cosmic structure and changes the relationship between the observed angular scale of fluctuations and their true physical scale. Because cosmologists know the size of certain features imprinted in the early universe, they can compare this known scale to the observed scale. The difference between the two reveals how the universe has expanded since that time. This comparison allows cosmologists to determine the relative contributions of matter and dark energy. The result shows that dark energy dominates the energy content of the universe, making up the largest component of the cosmic inventory. The cosmic microwave background also tells us about the geometry of the universe. Geometry refers to the curvature of space itself. If the universe were strongly positively curved, like the surface of a sphere, or strongly negatively curved, like a saddle, the patterns in the cosmic microwave background would appear distorted. Instead, observations show that the angular scale of fluctuations matches almost perfectly what would be expected if space were flat. In cosmology, flat does not mean empty or two-dimensional. It means that, on sufficiently large scales, the rules of Euclidean geometry apply. Parallel lines remain parallel, triangles sum to 180 degrees. The early plasma produced acoustic waves of known physical size. When their imprints are observed at a specific angular scale, this reveals that the universe is extremely close to flat. The slight deviations that could exist fall within incredibly small margins. This flatness supports the theory of inflation, which predicts that any initial curvature would be smoothed out by rapid early expansion. Polarization patterns in the cosmic microwave background reveal even more subtle aspects of the early universe. Temperature fluctuations alone cannot tell the full story of how photons last scattered before decoupling. But polarization reflects the direction of the electric field in the radiation and carries information about the geometry and motion of the early plasma. Polarization data confirm many conclusions drawn from the temperature map, including the scale of density fluctuations and the nature of acoustic oscillations. They also reveal the reionization history of the universe. After the first stars formed, their ultraviolet light reionized the surrounding gas. This reionization introduced new scattering events that left a signature in the large-scale polarization pattern. By studying this signature, scientists deduce when the first stars ignited and how quickly reionization took place. The cosmic microwave background provides a direct measurement of the initial conditions for structure formation. The tiny fluctuations recorded in the radiation represent the seeds from which galaxies, clusters, and cosmic filaments later grew. Their nearly scale-invariant distribution indicates that fluctuations were produced by a process like cosmic inflation, which stretched quantum fluctuations into macroscopic variations. The fact that these fluctuations follow a nearly Gaussian statistical distribution further supports this picture and restricts the types of inflationary models that are viable. The cosmic microwave background does not merely suggest inflation, it strongly constrains the physics that inflation must obey. Time also leaves its imprint on the cosmic microwave background through gravitational effects. As photons travel through the universe, they pass through regions of varying gravitational potential created by galaxies, clusters, and dark matter. These interactions slightly distort the cosmic microwave background in a phenomenon known as gravitational lensing. Lensing does not erase the original pattern, but alters it in ways that can be measured. By analyzing the lensing-induced distortions, cosmologists reconstruct the distribution of matter across the universe. This includes both ordinary and dark matter. The cosmic microwave background thus becomes a map not only of the early cosmos, but also of the integrated gravitational structure of the universe from decoupling to the present. The cosmic microwave background even sets limits on phenomena that have not yet been observed. For example, relic gravitational waves from inflation would produce a specific pattern of polarization known as B-mode polarization. Although searching for this signal is challenging, its detection would be profound. It would offer a direct window into the physics of inflation and the behavior of gravity at energy scales far beyond laboratory experiments. Although B-mode patterns from gravitational lensing have been detected, confirming inflationary B-modes remains an open goal. The fact that the cosmic microwave background holds the possibility of revealing such deep physics underscores its importance. Another insight the cosmic microwave background provides involves the baryon acoustic oscillations, the relics of sound waves in the early plasma. These oscillations produced characteristic scales in the distribution of matter. While the cosmic microwave background records the imprint of these waves at the moment of decoupling, the influence of these oscillations persists in the distribution of galaxies today. By comparing the patterns in the cosmic microwave background with galaxy surveys, scientists link the early universe to the structure we see billions of years later. This connection provides one of the strongest cross-checks in cosmology, confirming that a single physical story explains both ancient radiation and modern matter distribution. The cosmic microwave background also helps scientists understand the epoch of matter-radiation equality. This was the time when the density of matter became larger than the density of radiation, allowing matter to begin forming structures more effectively. The timing of this transition affects the shape of the cosmic microwave background power spectrum. By measuring the heights of peaks, cosmologists determined precisely when this equality occurred. This information constrains the density of dark matter, because dark matter contributes to gravitational pull, but not to radiation pressure. The cosmic microwave background becomes a tool for measuring components that cannot be seen directly. Even the degree of uniformity in the cosmic microwave background carries meaning. The fact that light from opposite sides of the sky has nearly the same temperature presents a puzzle. How could such distant regions, apparently never in causal contact, have nearly identical thermal properties? This puzzle is resolved by inflation, which posits that regions now separated by vast distances were once close enough to interact and reach equilibrium. The cosmic microwave background's uniformity thus serves as evidence for inflation's dramatic early expansion. Despite all that the cosmic microwave background reveals, it also contains mysteries. Certain anomalies, such as the cold spot or hemispherical asymmetries, do not yet have definitive explanations. They may be statistical flukes, or they may hint at new physics. Whether they signify something profound or simply reflect chance variation remains unknown. The cosmic microwave background, though deeply understood, still contains questions that keep cosmologists attentive and curious. Taken together, all of these insights illustrate a remarkable truth. By studying a faint glow preserved from the earliest era of cosmic clarity, we can reconstruct the universe's composition, geometry, evolution, and initial conditions. The cosmic microwave background transforms the sky into a scientific archive. It allows us to read the first chapter of cosmic history, not through imagination alone, but through direct observation. And perhaps, in the quiet of this moment, there is something deeply moving in the fact that the universe carries its own memory so faithfully. These ancient photons have traveled across expanding space to reach you here, offering a message from a time before stars existed. In listening to them, you become part of a continuity stretching across billions of years. The cosmos remembers its origins, and in its memory, you can find a gentle reminder of your place within its vast, unfolding story. Chapter 8: The Mysteries Hidden in the CMB. The cosmic microwave background is often described as the most precisely measured phenomenon in cosmology. Its spectrum matches that of a perfect black body to a remarkable degree. Its temperature fluctuations are mapped with extraordinary resolution. Its polarization patterns have been dissected with increasing sophistication. And yet, despite this clarity, the cosmic microwave background still holds mysteries that remain unresolved. Some are subtle anomalies, faint deviations from perfect statistical expectations. Others are deeper puzzles involving unexplained alignments or unusually cold regions. A few challenge aspects of the standard cosmological model, while others hint at physics that may lie beyond it. These mysteries are not flaws in our understanding. Rather, they are invitations. They remind us that even in a universe whose broad structure we understand well, there remain features that resist easy explanation. One of the most frequently discussed anomalies is the so-called cold spot. It appears as a region of the sky that is significantly cooler than surrounding areas, larger in angular size than typical temperature fluctuations, and somewhat deeper in amplitude. The cold spot lies in a region of the southern hemisphere of the sky, and its existence has been confirmed by multiple generations of cosmic microwave background experiments. Although temperature variations across the sky are expected to follow a random Gaussian distribution, the cold spot appears unusual in its size and depth. Various explanations have been proposed. One possibility is that it is simply an unlikely statistical fluctuation that occurred by chance. Given that the sky contains billions of pixels of temperature data, one unusual region is not impossible. Another possibility, however, is that the cold spot reflects a large region of the universe that is underdense, sometimes referred to as a supervoid. Light traveling through such a void would lose energy due to gravitational effects, creating a colder region in the cosmic microwave background. Yet, even if a void contributes to the cold spot, it may not fully explain its characteristics. Some researchers have suggested more exotic possibilities, such as non-trivial cosmic topology, interactions with textures or topological defects produced in the early universe, or remnants of bubble collisions from phases of inflation. These ideas remain speculative, and no consensus has been reached. The cold spot illustrates a fundamental aspect of science. Anomalies often persist at the edge of understanding, acting as signposts, pointing either toward deeper truths or toward the natural scope of randomness in a large data set. Another mystery arises from an unexpected hemispherical asymmetry in the cosmic microwave background. Ideally, the temperature variations should appear statistically the same in all directions. The universe on large scales is expected to be isotropic, meaning there should be no preferred direction in space. Yet, multiple analyses have revealed that one half of the sky appears to have slightly greater temperature fluctuations than the other. The asymmetry is subtle, but it is persistent across data sets and frequencies. It seems to favor one hemisphere, giving rise to what is sometimes called the dipole modulation anomaly. This asymmetry has various proposed explanations. It might reflect the kind of random fluctuation that inevitably occurs when sampling a finite region of the universe. Or it might suggest something deeper, such as a deviation from isotropy or an imprint left behind by the early universe. Some inflationary models predict that the universe could contain large-scale features originating from correlations stretched across immense distances. If so, the hemispherical asymmetry might be a faint signature of physics beyond the simplest inflationary scenarios. Whatever the underlying cause, this anomaly challenges the notion that the early universe was perfectly uniform at the largest scales. A related puzzle involves what some researchers poetically call the axis of evil. This refers to a surprising alignment of low-order multipoles in the cosmic microwave background. In simple terms, certain long wavelength patterns in the temperature distribution appear oriented along a particular direction in the sky. These patterns include the quadrupole and octupole components, which, in a statistically random universe, should be oriented without any preferred direction. Instead, they appear slightly aligned with each other, forming an anomalous preferred axis. This alignment has sparked debate because it challenges the foundational assumption that the universe has no inherent directional structure on large scales. Some scientists have argued that the alignment may result from residual contamination from the Milky Way or other foreground emissions. Yet extensive analysis has attempted to remove such contamination, and the alignment persists. It is unclear whether this feature reflects a genuine cosmological phenomenon or merely a coincidence amplified by our sensitivity to rare patterns. The axis of evil remains an intriguing unsolved question, one that highlights the delicate intersection between statistical analysis, cosmological interpretation, and the temptation to read significance into patterns that may arise from chance. Another mystery involves the near absence of correlations at very large angular scales. When the cosmic microwave background temperature map is analyzed for patterns separated by large angles, regions of the sky more than 90 degrees apart, the level of correlation is far lower than expected. This lack of correlation seems surprising because theoretical models predict that fluctuations should exist across all scales. Yet the observed universe shows a curious deficit in these very large angular correlations. This anomaly might suggest new physics, perhaps involving the largest possible scale at which inflation operated. It could also reflect a feature of the observable universe's shape or boundary conditions. Alternatively, it may simply be an unusual statistical feature that arises rarely but naturally in a universe with random fluctuations. Despite intense scrutiny, no single explanation has emerged. The puzzle persists, inviting deeper investigation into the physics of inflation and the global structure of space-time. The cosmic microwave background also reveals hints of asymmetry in polarization patterns. While temperature fluctuations have been mapped with great precision, polarization introduces additional complexity. In particular, E-mode polarization behaves as expected, matching models derived from scattering in the early universe. But B-mode polarization introduces deeper questions. Although much of the observed B-mode signal results from gravitational lensing of E-modes by large-scale structure, a faint additional component may exist at the largest scales. Detecting this component is exceptionally challenging because dust emission from the Milky Way can mimic or obscure the signal. If such a component is eventually confirmed, it may represent gravitational waves from inflation, offering direct evidence of physics from the earliest moments of cosmic history. But until measurements reach higher precision, the interpretation remains uncertain. Another intriguing feature hidden within the cosmic microwave background involves potential non-Gaussianities. The The simplest inflationary models predict that fluctuations should follow a Gaussian distribution. Observations show that this prediction holds remarkably well, but subtle deviations may exist. Some analyses hint at possible non-Gaussian patterns that could be signatures of multi-field inflation, interactions between quantum fields, or other exotic processes. Although these hints are not yet statistically robust, they offer tantalizing possibilities for probing physics at energy scales beyond anything accessible in laboratory experiments. The cosmic microwave background also intersects with mysteries that come not from anomalies but from silence. For example, if the universe contains primordial magnetic fields or exotic particles that decay over cosmic time, they might leave faint but detectable imprints in the cosmic microwave background. So far, no such signals have been definitively identified. Yet the absence of these signatures imposes strong constraints on theories. The cosmic microwave background becomes not only a record of what happened, but also a record of what did not happen, limiting the range of possible early universe physics. Even the process of reionization, when the first stars and galaxies lit their surroundings with ultraviolet light, leaves behind subtle footprints in the cosmic microwave background. Large-scale polarization patterns reveal when reionization occurred and how rapidly it progressed. Although current measurements provide strong clues, uncertainties remain. Reionization was a complex and extended process, shaped by the first generations of stars and the emergence of early galaxies. The cosmic microwave background tells part of this story, but much remains unknown. These unknowns weave themselves into the broader tapestry of cosmic mysteries. Perhaps the most profound mystery embedded in the cosmic microwave background concerns the initial conditions that preceded it. Inflation provides a compelling framework for explaining the uniformity and flatness of the universe, as well as the origin of density fluctuations. Yet inflation itself raises questions. What caused inflation to begin? How long did it last? What field or fields drove it? Did inflation end everywhere simultaneously? The cosmic microwave background offers indirect clues, but it cannot yet reveal the full pre-inflationary story. The universe before decoupling is visible only through inference. Whatever preceded the moment of transparency remains hidden behind the veil of the early plasma. The mysteries of the cosmic microwave background remind us that science is not a closed book. It is a living process. Each anomaly, each unexplained alignment, each unexpected absence or faint suggestion of new physics reveals that the universe still holds secrets. Rather than undermining our understanding, these mysteries enrich it. They challenge researchers to refine models, develop better instruments, and push theories to their limits. The cosmic microwave background is at once the most thoroughly studied and most mysteriously layered signal in all of cosmology. And perhaps as you sit with these enigmas, there is comfort in recognizing that even the universe, vast and ancient, carries peculiarities and imperfections that resist immediate explanation. The cosmos is not a flawless machine. It is a story still unfolding. These faint anomalies scattered across the sky remind you that not every question has an answer yet, and not every mystery needs to be solved tonight. In their quiet persistence, they echo something human, the sense that wonder and uncertainty are companions, and that there is peace in letting the universe remain, just for a moment, beautifully unresolved. Chapter 9. The Future of the CMB, How It Will Change Over Trillions of Years. The cosmic microwave background is often described as a relic of the past, a silent remnant of an era when the universe first became transparent. But the cosmic microwave background is not frozen in time. It evolves, it cools, it shifts, it fades. Like everything else in the cosmos, it has a future as well as a past. And that future extends across timescales so vast that human language struggles to contain them. To understand how the cosmic microwave background will change over trillions of years is to confront the long-term destiny of the universe itself. The same expansion of space that once stretched photons into the microwave range continues today and will continue into the far future. The cosmic microwave background will slowly transform until eventually it becomes undetectable even with the most sensitive instruments imaginable. The present temperature of the cosmic microwave background is just a few degrees above absolute zero. This temperature reflects the immense stretching of space that has occurred since the moment of photon decoupling. As the universe expands, the wavelength of each photon increases, reducing its energy. For the cosmic microwave background, this means a continuous drift toward longer wavelengths. In the far future, the radiation will shift from the microwave region into the radio region, with wavelengths growing to lengths measured not in millimeters, but in meters, kilometers, and eventually beyond. The photon temperature will steadily decrease, approaching absolute zero but never reaching it. This slow cooling mirrors the relentless increase in the scale factor of the universe. The reason this transformation occurs lies in the fundamental properties of photon propagation in an expanding space-time. Photons always travel at the speed of light relative to local space-time, but the expanding geometry of the universe stretches their wavelengths. This stretching is not caused by the photons themselves losing energy through interactions. Instead, it is the fabric of space that imposes this evolution. The energy of each cosmic microwave background photon decreases inversely with the expansion. Over trillions of years, as the expansion accelerates due to dark energy, the cooling will proceed even more rapidly than during earlier cosmic eras. The cosmic microwave background will also become increasingly difficult to detect due to the evolution of the universe's structure. Today, the cosmic microwave background can be observed from nearly every region of space because the universe remains largely transparent to microwave photons. Neutral hydrogen absorbs only specific frequencies, and the cosmic microwave background occupies a range that mostly passes through intergalactic matter unhindered. But the transparency of the universe is not static. As galaxies evolve, stars die, and cosmic structures change, the distribution of matter will alter the propagation environment. In the far future, galaxies will drift apart as cosmic expansion accelerates. Beyond certain time horizons, gravitationally unbound galaxies will recede faster than light relative to each other due to the expansion of space. From the perspective of any observer, distant galaxies will fade below detectability and eventually disappear beyond the observable horizon. The cosmic microwave background, too, will be affected by this phenomenon. The observable patch of the cosmic microwave background will shrink, not because the radiation ceases, but because the co-moving region of space that can send photons to an observer becomes smaller as expansion accelerates. Eventually, only a diminishing fraction of the cosmic microwave background sky will remain visible. The cosmic microwave background will not simply grow faint, its original structure will also be increasingly distorted. Over time, gravitational lensing by evolving cosmic structures will shift and smear the anisotropy pattern. But more importantly, the anisotropies themselves will be stretched beyond scales that can be resolved. The characteristic peaks and troughs that encode early universe physics will eventually be redshifted to such low energies that distinguishing them from noise becomes an extraordinary challenge. Even with perfect instruments, the anisotropies will become washed out by the sheer stretching of wavelengths. Another influence on the future of the cosmic microwave background arises from entropy production within the universe. Processes such as star formation, supernova, black hole accretion, and dust emission all generate photons at various wavelengths. Although these photons are far less uniform than the cosmic microwave background, they contribute to the total radiation field. In the present epoch, the cosmic microwave background is the dominant form of background radiation by energy density. But in the distant future, as the cosmic microwave background cools and stretches, other radiation sources will eventually surpass it. This does not erase the cosmic microwave background, but it makes its detection more difficult, buried beneath newer, more local emissions that are not relics of the early universe. Black holes will also influence the future radiation environment. As stars finish burning their nuclear fuel and galaxies enter an era dominated by compact objects, black holes will slowly evaporate through Hawking radiation. This radiation is extremely faint and cold, but over unimaginably long timescales, it becomes significant relative to the fading cosmic microwave background. In the far future, when the universe is dominated by dark energy and only the remnants of stellar evolution persist, Hawking radiation from evaporating black holes will constitute one of the primary radiation sources. At that time, the cosmic microwave background will have cooled to such an extent that its photons possess wavelengths so long and energies so small that they become functionally undetectable. The detectability of the cosmic microwave background is also influenced by the cosmic event horizon created by dark energy. As expansion accelerates, a horizon forms beyond which events can never influence a given observer. Photons emitted today from extremely distant sources will never reach us. Similarly, in the far future, photons from most of the cosmic microwave background sky will lie beyond this horizon. The observable universe will shrink not in physical size, but in causal connectedness. The local cosmic environment will become increasingly isolated. The cosmic microwave background will be limited to a tiny patch of the sky, slowly redshifting toward wavelengths so large that they could span entire galaxies. Eventually, in the deep future, there will come a time when the cosmic microwave background's temperature is so low that even the most advanced civilization, if such a civilization exists, would struggle to detect it. The radiation will not disappear, but its photons will be stretched so dramatically that they carry almost no measurable energy. The cosmic microwave background will have transitioned from a rich field of cosmological information into a faint whisper, drifting through an ever-expanding void. It is worth reflecting on how much information will be lost to future observers. At present, the cosmic microwave background allows cosmologists to determine the age, composition, and geometry of the universe with extraordinary precision. But in the far future, when only a tiny fraction of this radiation remains observable, such measurements will become impossible. Civilizations living in isolated, gravitationally bound regions, perhaps clusters of stars long after galaxy mergers, will not be able to see beyond their local cosmic environment. They may conclude that the universe is static or eternal because they will lack access to the evidence of cosmic expansion. Without the cosmic microwave background, many of the clues that reveal the true nature of the cosmos will vanish. The universe will appear smaller, quieter, and more limited in scope. Its great origin story will be obscured by the very expansion that once made it intelligible. This loss of cosmic context is not a contradiction of science. It is a feature of a universe governed by dark energy and expansion. Cosmology itself is time-dependent. The universe reveals different truths to observers depending on when they exist. We live in a privileged era, not early enough to be engulfed in opacity, not late enough to have lost the cosmic microwave background to the darkness of accelerating space. We exist at a time when the universe's earliest light is still visible, still measurable, still full of stories. Future observers will not share that opportunity. Yet even in that distant era, the cosmic microwave background will remain a part of the universe's fabric. Its photons will continue to drift, silent and stretched, through an ever-expanding cosmos. They will not vanish. They will simply become more spread out, more diffuse, more subtle. Their journey will continue endlessly, each photon traveling through the widening emptiness of a universe that is slowly cooling toward its final state. And perhaps there is something quietly beautiful in this long decline of the universe's earliest light. The cosmic microwave background has carried the memory of the beginning across billions of years. It has survived every transformation the universe has undergone. Its future, slow fading, endless stretching, is a reminder that everything, even the universe's own memories, changes with time. As you reflect on this distant future, you may find comfort in the thought that even the faintest trace of beginnings continues its journey. The cosmos holds its history with exquisite patience, and in the quiet of this moment, you too can rest in the knowledge that everything unfolds in its own time, carried gently forward by the expanding fabric of existence. Chapter 10. Why the Oldest Light Matters, a quiet reflection on origins. There's a deep and quiet power in the idea that the universe carries a memory of its own beginning. The cosmic microwave background is that memory, preserved in the form of ancient light that has traveled across expanding space for nearly the entire history of the cosmos. It is the oldest freely propagating radiation we can ever observe. Earlier eras are hidden behind the veil of opacity that existed before atoms formed, and later epochs are layered with the complex structures that emerged as matter clumped into stars and galaxies. The cosmic microwave background occupies a unique place in the history of the universe. A moment when everything had just become visible, when the cosmos first opened its eyes. Understanding why the oldest light matters requires understanding what it represents. The cosmic microwave background is not simply a relic. It is the direct imprint of a universe transitioning from chaos to clarity, from a hot plasma of charged particles to a vast expanse filled with neutral atoms. Before recombination, photons scattered constantly off free electrons. There was no transparency, no direction from which light could travel freely, no way for radiation to carry information from one part of the universe to another. When electrons bound to protons and neutral hydrogen formed, photons decoupled from matter and began their journey across space. That moment, when the fog lifted and the cosmos became transparent, is frozen into the cosmic microwave background. The significance of this transformation cannot be overstated. For the first time, the universe possessed a visual identity. Photons that had been trapped now streamed outward, crossing vast distances without losing their connection to the conditions in which they were released. They carried with them patterns imprinted by tiny density variations in the early plasma. These variations reveal how matter was distributed at the dawn of cosmic history. They are the earliest accessible fingerprints of structure formation. And through them, we gain insight into the fundamental forces, particles, and processes at work when the universe was still young. The cosmic microwave background also matters because it provides a foundation for modern cosmology. Many of the core parameters describing the universe, its age, its composition, its geometry, derive directly from measurements of this ancient radiation. Without it, our understanding of cosmology would be far less certain. Before the cosmic microwave background was detected, cosmological models included a wide range of possibilities. The universe might have been infinitely old or relatively young. It might have been curved strongly or nearly flat. Matter could have dominated, or radiation, or some unknown substance. The discovery of the cosmic microwave background transformed cosmology from a speculative field into a quantitative science. By studying this radiation, scientists have determined that the universe is approximately flat on large scales, meaning that its spatial curvature is extremely close to zero. This finding supports the inflationary model, which posits that the early universe underwent a brief but dramatic period of rapid expansion. Inflation explains why the cosmic microwave background is so uniform across the sky, even in regions that appear to be causally disconnected. It also explains why the universe's geometry appears flat, as enormous expansion would smooth out any initial curvature. Measurements of the cosmic microwave background provide some of the strongest evidence for inflation and shape our understanding of the universe's earliest moments. The cosmic microwave background also reveals the composition of the universe with surprising precision. The relative heights of acoustic peaks in the temperature-power spectrum encode the amounts of ordinary matter, dark matter, and radiation present during the time of recombination. These measurements show that ordinary matter makes up only a small fraction of the universe's total mass energy content. Dark matter contributes much more, shaping the formation of galaxies and large-scale structure, while dark energy drives the accelerated expansion of space. The cosmic microwave background allows scientists to measure these components independently and accurately, anchoring our understanding of cosmic evolution. Another reason the oldest light matters is that it preserves evidence of processes that occurred at energy scales far beyond what can be achieved in particle accelerators. The density fluctuations visible in the cosmic microwave background are thought to originate from quantum fluctuations during inflation. These tiny variations, stretched to cosmic scales, form the seeds of all later structure. The fact that these fluctuations appear nearly Gaussian and scale invariant provides key constraints on models of inflation. No laboratory experiment can reach the energies present in the earliest moments of the universe. Only by studying the cosmic microwave background do we gain insight into that extreme epoch. The cosmic microwave background also matters because it ties together different eras of cosmic history. It records the universe as it was when it first became transparent, but it also contains echoes of events that unfolded long afterward. Gravitational lensing, by large-scale structure, distorts the patterns in the radiation, allowing scientists to reconstruct the distribution of matter over billions of years. Signatures of reionization reveal when the first stars formed and how they altered the surrounding gas. The alignment and orientation of temperature and polarization patterns reflect processes that occurred both before and after decoupling. The cosmic microwave background is not merely a snapshot. It is a dynamic record that continues to interact with cosmic structure as it travels toward us. The cosmic microwave background's importance is also philosophical. It illustrates the profound connection between the microphysical world of particles and the macrophysical world of galaxies and cosmic webs. The density fluctuations imprinted in the cosmic microwave background arise from quantum processes operating at the smallest scales. Yet these fluctuations eventually gave rise to structures hundreds of millions of light-years across. The cosmic microwave background embodies this unity of scale, showing that the immense complexity of the universe traces its roots to tiny, primordial variations. Another aspect of its significance lies in its universality. Every observer, no matter where they are in the cosmos, sees their own cosmic microwave background, centered on their location, shaped by their cosmic horizon. If an observer lived on a distant galaxy billions of light-years away, they too would detect the cosmic microwave background with similar patterns and peaks. The details might vary slightly due to gravitational lensing or motion, but the fundamental imprint would be the same. This universality reflects a deeper truth. The cosmic microwave background is not local. It does not belong to Earth or to the Milky Way. It belongs to the universe as a whole. It is the earliest shared inheritance of all cosmic observers. Because the cosmic microwave background is so fundamental, its eventual fading carries a bittersweet implication. In earlier chapters, we explored how the cosmic microwave background will continue cooling and stretching as the universe expands. In the far future, when wavelengths become so long that they stretch across galaxies, the cosmic microwave background will become effectively undetectable. Civilizations living in distant epochs may not realize that their universe had a beginning in the hot plasma state. Without the cosmic microwave background, they will lack the evidence that anchors modern cosmology. The universe's own memory will still exist, but it will be buried beneath expansion and time, silent to all but the most extraordinarily advanced observers. This realization deepens the significance of the cosmic microwave background for us, living during a privileged cosmic window when its signal is still bright enough to study. We exist at a time when the earliest light remains accessible, when the universe's infancy is still visible across the sky, when scientific instruments can still detect and decode its patterns. The cosmic microwave background will not always be so generous with its information. In the grand timeline of cosmic history, the era of observability is brief. And perhaps, in this quiet awareness, you can feel something deeply human. The oldest light matters not only because of what it reveals scientifically, but because of what it evokes. It reminds you that the universe has a history and that you are living within it. It reminds you that you occupy a moment suspended between cosmic dawn and cosmic dusk, with the ability to look backward further than countless generations who may come after. It reminds you that even across immense distances and unimaginable stretches of time, the universe carries its earliest memories gently, offering them to anyone who cares to look. And as you breathe out and let the weight of the day drift away, you may find comfort in knowing that you too are made of ancient light and matter shaped by the same forces that once rippled through the early cosmos. The universe remembers where it came from, and in witnessing that memory, you become part of its ongoing story, quietly, peacefully, endlessly unfolding. My friend, thank you for spending this quiet journey with me. If you're still awake and your curiosity is still glowing, you can float into another video waiting for you here. It's just as gentle and just as vast. But if your eyes are heavy now, then I wish you the softest sleep and the sweetest dreams among the stars.